Welcome, everyone. This is section 3.3, where we will be covering measures of relative position. So we are going to be discussing how we can be explaining or discussing various data relative to each other. So let's go ahead and get started, as always, with some definitions here. So starting out with percentile, the percentile of a data value is a way to think of this is if I were to divide my data into 100 equal pieces, where would those data values be? To find the data value that corresponds to a given percentile, we use this formula given here where L equals N times P over 100, where L is the location of the pth percentile in the ordered array of data values, N is the number of data values in the sample, and P stands for the pth percentile. So the 57th percentile, P would be 57. Now, I'm just going to do a little bit of algebra on this. If L equals N times P over 100, and let's suppose I want to solve for P, I could multiply both sides by 100, get 100L equals N P, divide both sides by N, and I would see that P equals 100L over N. So this is another formula we're going to make use of here, where we want to find the percentile given L and N. Okay. Some things to note here. When using the formula to find the location of the percentile's value in the data set, two rules you need to follow. First, if the formula results in a decimal value, the location is the next whole number. If the formula results in a whole number, the percentile's value is the mean of the next two. So for example, so of that one and the next one. So for example, if you end up with 47, then it would be the mean of the 47 and 48th entry, okay? So let's take a look at an example here to see how we can find the percentile. So a car manufacturer is studying the highway miles per gallon for a wide range of makes and models of vehicles. The following stem and leaf plot contains the average highway miles per gallon for each of the 135 different vehicles the manufacturer tested. So we have the stems over here on the left side with our leaves over on the right. The key is that 12 to 1 gives us 12.1. So that means this number on the left here is the whole number part, and the number on the right is the tenths place after that. Okay. Then this problem says A, find the 10th percentile, and B, find the 100th percentile. So let's get started on A here. Now, I know I'm going to be making use of the formula L equals N times P over 100. So what I need is I need N and I need P. So N here is the number in the sample. I know it's 135 because that's what they tell us. Okay. The percentile, they also tell us we're looking for 10. So P equals 10. So I'm just going to plug this in. This is going to be L equals 135 times 10 over 100. Well, 10 divided by 100 is 0.1 times 135 is 13.5. So I get a decimal, I round that up. That tells me that the location I'm looking for is the 14th entry. So I need to find the 14th entry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I see that it is 17.3 miles per gallon. Okay, so I simply found the 14th entry in my data list. Note that it needs to be an ordered array. So I need to make sure that it is ordered before I go and count which one it is. Excellent. Then for B, the same exact idea here. L equals N 135 times P 20 over 100. Well, this is going to be twice that, so I get 27. Now, I'm not going to just hop on over, look at the 27th entry, because remember, if you have a whole number, you need to take the mean of the 27th and 28th data values here. So if I took a look, 17.3, this was the 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, so my 27 and 28th data values are 19.2 and 19.3. So my average of 19.2 plus 19.3 over 2 is midway through that, and I find 19.25 miles per gallon. And there we go. Okay. Our overall rule that we're looking for here is just, hey, is it a decimal? If so, go up to the next number. If it's not a decimal, that is to say, if it's a whole number, take the mean of that value and the next one. Okay. Now, as I previously said here, our other formula we can use is this one here. So let's suppose that we are given this one here. It says, in the data set from the previous example, the Nissan Xterra averaged 21.1 miles per gallon, which represents the 48th and 49th value. Okay, so I know that this is shared with the 48th and 49th value. If it's shared, we're going to use the higher one. So we are going to be looking at the 49th for our location, L. So my P equals 100 times L, in this case 49 over 135. So I'm going to take 100 times 49 divided by 135. And I'm going to round this to the nearest one here. I find this is approximately 36.3%, but I want to round that to the nearest percentile here. So this is going to be the 36th percentile. Okay. So all I did here was I simply made use of this formula here when I'm trying to find the percentile. Okay. So if we're trying to find our percentile, we use that formula. And a little bit of a thing to note, we had the 48th and 49th share the same value. So we are looking at the 49th one there. Okay. Now that we've talked about percentile, let's go ahead and discuss our next grouping of numbers, which are quartiles. So again, to save you my handwriting here, let me just paste this directly from my notes. Quartiles are values that divide an ordered array into, well, 4 equal parts, equivalent to the 25th, 50th, and 75th percentile. We have the first, second, and third quartile. The first quartile, 25% of the data are less than or equal to this value, so it's the 25th percentile, second quartile, 50, third quartile, 75. Okay. Now, if we want to find the quartiles, all that I need to do is simply calculate the percentiles of each. But that seems like a little bit of unnecessary work. So what I'm actually going to do is I am going to note here. So again, there are 2 ways we can go about calculating this. Our first way is to calculate the 25th percentile, the 50th percentile, the 75th percentile. But the other way that we can do this is we can note, if I am looking at the percentiles here, so if I'm looking at the 25th, 50th, and 75th percentile. Another way of saying this is the 50th percentile is the median. It's my middlemost entry, right? Because half the entries are less than it. Okay, so the 50th is equivalent to my median. What I can then do is if I then exclude this median, this is the median of data values less than the median. because 25 is half of 50. So if I look at my data set just from 0 to 50th percentiles, my mid of that is going to be my 25th. Similarly, 50 to 100 is going to be the 75th. So this is the median of the data. Greater than the median. Wonderful. Now that we know that, what this allows us to do is, well, we can just look at medians, and we have a very wonderful tool for calculating the medians. Well, for calculators. So all I'm going to do is I'm going to clear out my lists from previous examples and just fill in with the data we've got here. 60, 62, 63, 65, 65, 67, 70, 71, 75, 78, 79, 80, and 81. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let me just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It appears as though I've missed a number. So let me just go back through here. 60, 62, 63, 65, 65, 67, 70, 71. I missed my second 71. So I'm just going to put that back into here. Always good to double check and make sure that you've included all your data values. So then I'll go to calc, one variable stats, clear out that frequency list because I don't need to make use of it. And now I'm just going to scroll down and it will let me know several things here: the min, the first quartile, the median, the third quartile, and the max. So I can see directly all of these things that I'm looking for. Now you'll note that we also have the min and the max. When I put all of those together, this gives me what is called the 5-number summary. The 5-number summary is given to you by the min, the first quartile, the median, otherwise known as the second quartile, the third quartile, and the max. If we just have these 5, we can make use of what's called a box and whisker plot. I'll show you what that looks like in a bit, but go ahead and take a look at B, double check it with your calculator, make sure you have all those entries in. All right. Then let's go ahead and take a look at our next concept here. So again, our 5-number summary is our min, first quartile, median, third quartile, max. So in this case, 60, 65, 70.5, 78, and 81. Our next concept to discuss is that of the inner quartile range. The inner quartile range is the range of the middle 50% of the data. We calculate it by simply taking our third quartile minus our first quartile. Okay. We will make use of this when we are attempting to find outliers. But before then, I mentioned that I would discuss how we can do a box and whisker plot given our 5-number summary. And for this, let me get you a better image of that. So I'm just copying this straight from my notes. Okay. Now, if I take a look here, my 5-number summary is actually visible on this box and whisker plot. It's called a box and whisker plot because we got a box and we've got these little whiskers. This here corresponds to my min. This is my first quartile. This is my median. This is my third quartile, or Q3 if you prefer. And this here is my max. Now, sometimes you will see like a dot in here. If they do put a dot somewhere on there, that is generally what they're doing for the mean, but not necessary for it to be shown on a box and whisker plot. So when you are constructing a box and whisker plot from data, what you're doing is you are finding the 5-number summary, which again, to find your 5-number summary, you can either calculate those percentiles, or you can find the median of the data set less than the median of the data set greater than the median. You can plug it into your calculator. All of these are perfectly reasonable ways for you to calculate the values. And then you'll simply plot your box being your first quartile to your median to your third quartile with your whiskers on your min and your max. Okay. So then I mentioned that we use our inner quartile range for finding outliers. Well, how do we do that? We find at any outliers are any data values that lie outside of the following interval. So the interval goes from the first quartile minus 1.5 times our inner quartile range to our third quartile plus 1.5 times our inner quartile range. If you are a data value and you do not belong to this interval, then you are considered too far outside of the range of our data set, and thus you are considered to be an outlier. Okay. So let's take a look at this example here to see if we can identify an outlier, if any. It's possible that our data set doesn't have any outliers, and that's okay. The following data represents commuting distances in miles for a sample of 30 summer interns. Okay. Now, fortunately, they give us to us sorted, but that doesn't particularly matter. So I'm just going to go ahead, plug this data in, 0.8, 1.3, 0.9, 2.1, riveting content as I enter values into my calculator. Feel free to skip a bit ahead as I'm entering these in, or wait and enjoy this clicking sound. Calculator ASMR right here. I'm sure some people that are watching just cringed a little bit. Oh, let me make sure I haven't skipped any data values here. 0.8, 1.3, 1.9, 2.1, 2.4, 2.4, 3.8, 0.9, 5.0, 7.1, 1.2, 1.4. Okay, good. 11.7, 12.3, 12.7, 12.9, 13.0, 13.6, 14.2, 15.1, 19.3, 20.3, 22.1, 22.5, 24.8, 28.5, 29.4. The end is in sight, 33.7, 39.8, and the coup de grace, 49.6. Whew. So now I'm going to go ahead and do my one variable stats, calculate. I'm going to take a look here. My first quartile is 3.9. My third quartile is 22.1. So I'm going to go ahead and do 22.1 minus 3.9. That will give me my inner quartile range. So my inner quartile range, which is of course my third quartile minus my first quartile, is 18.2. All right. Now I need to use this to identify any outliers. So what I'm going to do is I'm going to take 1.5 times 18.2. I'm going to add this number to my third quartile and subtract it from my first quartile. So I'm going to take 3.9 minus 27.3. Well, negative 23.4. So things need to be within negative 23.4 to my 22.1 plus 27.3, which is 49.4. So I need to check to see, are there any data values that lie outside of this interval? Well, I take a look here and I note this 49.6 is sticking out. So 49.6 is an outlier. And there we go. So that's all I do when finding an outlier. Okay. Now let's go ahead and change gears a little bit. The next thing I want to talk about is the concept of what is called a z-score, otherwise z-score, otherwise known as a standard score. Okay. Now, let's go ahead and give you our definitions here. Our standard score, or z-score as it's more commonly referred to, is simply the number of standard deviations above or below our mean a particular data value is. So I take that data value, subtract my mean, then take that result and divide by my standard deviation. What that will do is it will show me, hey, if it's negative, you're some number of standard deviations below my mean. If you're positive, then you are above the mean. When we are looking at z-scores, it is convention to round our z-scores to 2 decimal places. Now, the reason for that, unfortunately, is unclear to us at the moment. The reason is because we want to make use of a z-score table, which has a percentile that corresponds to each of our z-scores. But to use that table, we need 2 decimal places. So that's where it comes from. It's just a rounding artifact for our method of making use of these. Okay. But these formulas are what we're going to use, and we are going to use them a whole lot a little bit later on in the course. But now let's just see how we can calculate z-scores. If the mean score on the math section of the SAT is 500 with a standard deviation of 100 points, what is the standard score, or z-score, for a student who scored a 630? So for this, my z equals my data value, 630, minus my mean, 500, divided by my standard deviation, 100. 630 minus 500 is 130. Divided by 100 is 1.3. What this tells me then is that the student's z-score, or their student's score, is 1.3 standard deviations above the mean. Okay. Now, when we are looking at z-scores, these are good for telling us who is or what is a higher relative value compared to their peers. Because when we're comparing directly things to their peers, we want to normalize them. That is to say, we want to ground them relative to those around them. So if I am comparing a data value from one set, data value from another set, I'm not just going to look at their raw values. Rather, what I'm going to do is I am going to compare the z-score of those values to determine which one actually represents a higher percentile and thus a higher relative value. To show you what I mean, let's go ahead and take a look at an example here. This one says Jody scored an 87 on her calculus test. Good on her. Incidentally, calculus is a wonderful course. You should take it if you've not already. If you don't need to, I still recommend it. It's very fun. You might even be able to have it with me, your favorite instructor. Anyway, Jody scored an 87 on her calculus test and was bragging to her best friend about how well she had done. She said that her class had a mean of 80 with a standard deviation of 5. Therefore, she had done better than a class average. Her best friend Ashley was disappointed. She had scored only an 82 on the calculus test. The mean for her class was 73 with a standard deviation of 6. Who really did better on the test compared to the rest of her class, Jody or Ashley? So at first blush, you might say, aha, Jody scored an 87, Ashley scored an 82, Jody did better. But remember, when comparing them to the class, let's convert them to z-scores in order to compare them more directly. So here my z-score is going to be my x for Jody, 87, minus my mean, 80, divided by 5. This is 7 over 5, which don't need a calculator for this one. It's 1.4. Though if you do need a calculator, that's okay too. Then for this next one, I have 82 minus 73 over 6. 82 minus 73 is 9 divided by 6. If my math checks out, this is 1.5. So we see that actually Ashley's score corresponded to a higher z-score. Thus, relative to her peers, Ashley did better. So although Jody had a higher raw score, Ashley did a better job relative to her peers. Okay. That is all that I wanted to cover out of this section. As always, if you have any questions, do be sure to let me know. Otherwise, I will see you in the next video.